so quizzes on Monday. It'll cover the second part of chapter 2. That's just capacitors. So on the exams, that's almost all completely exam 2. But I think spring 19 and spring 21 both have questions about capacitors. Let me just show those to you. So you go to the website, spring 19 and spring 21. So spring 21, if you notice on exam 1, there are, I think this is the one, yeah, there are a few questions about capacitors. So that's spring 21. Sorry, y'all. Get up here. So spring 21, and then also, there we go. And then also spring 19, if you just go back a little bit in exam 1, you'll see that there are a few questions about capacitors. So just be aware that those questions will be on your quiz too. Let's see, where is it? Right here for number 13. This is spring 19, number 13 down through number 15. Just make sure you're reviewing those questions too so that you're not surprised. But I will pull questions from those 5 years of exams. That's exam 2 from spring 18 up to the last semester, spring 22, and then 18, 19, 20, 21, yeah. And then also from exams 1 from spring 19 and spring 21. There aren't that many questions, honestly, so I'm hoping that this is a really good quiz, that y'all do really well on it, because on each exam there are only maybe 5 or 6 questions for you to pull from. But some of those questions are difficult, so especially the capacitor circuits, that especially if they're new to you, and they're new to everybody, then they're going to be difficult. So we'll take some practice to be able to master those. I'm okay with just memorizing them, but if you just memorize those 25, 30 questions or whatever, that's fine by me. But of course, you'll do a lot better if you understand them, and that'll help you on the exam too. But I do really a good showing. Don't worry right now about the free response. We'll do more of those as that time gets closer. But I do want to spend some time just on the circuits. Is that okay? Do a few circuits. So this is spring 22. Let's look at this one. This one is a simpler one, number 3, finding the voltage across C1. The first thing that you would do, and remember, there is an easy way and a hard way to do these. And the hard way will always work. The easy way will often work. Okay, so I like to know how to do the hard way first. The first thing that you do is find the equivalent capacitance. So find CEQ. And in this case, they're in series, so that's 1 over 2 plus 1 over 4. That's 2/4 plus 1/4 is 3/4. So that's an equivalent of 1 over 3/4 or 4/3 microfarads. Hey, Octavia. I like to redraw my circuit each time. So I would redraw this circuit as a battery and one single capacitor, 9 volts, and 4/3 microfarads. So this is my V, this is my C. The way that I usually do this is I'll always include the units. That way I don't have to write both the variable and the units, and then the units clue me in as to what that value is. So I wrote 4/3 microfarads to tell me that that is my capacitance. But you could write C equals 4/3. I just find it's easier to write the units. Then the next step, in this case, when I have capacitors in series and I want to know the voltages across them, is to find the voltage, or find the charge. Find QEQ. That's equal to C times V. That's 4/3 microfarads times 9 volts. The 3's cancel and gives me 12 microcoulombs. So that's the second step, is to find QEQ. And then remember that capacitors in series have the same charge, right? They have the same charge, and they have the same charge as the equivalent capacitance. So both of these capacitors, which have an equivalent of the 4/3 microfarads, have a charge of 12 microcoulombs. And then anytime you get two quantities on a capacitor, you can always find the third quantity. So this is Q, that's C. V is equal to Q divided by C. So I have 12 divided by 2 is 6 volts. 12 divided by 4 is 3 volts. Recognizing that 6 plus 3 is equal to 9 volts, and so that checks with what the battery should be. Then I go back, let's see, I'm looking for the voltage across C1. So across C1 would be 6 volts. That's the hard way. That way is always going to work on any circuit, no matter what the numbers are. But there is an easier way, and often, almost always, there's an easier way to answer these questions where you don't really have to do any of these steps. That you look at the capacitors, you see that they are different by a factor of 2. Not a difference of 2, but by a factor of 2. If I'm saying that 4 divided by 2 is equal to 2, so one capacitor is twice that of the other. And so then the big capacitor will have a voltage that's 1/2 of the small capacitor. Remember that little sub rule that I gave y'all? That big capacitors have small voltages and small capacitors have big voltages. So then I could say that the big capacitor has a voltage that is twice the voltage. Oh, so that looks like it's 2 volts. Let me erase that. This capacitor has a voltage that's twice the voltage of that capacitor, or excuse me, that is half the voltage of C1, and they have to add up equal to 9. So this has to be 3 volts, this has to be 9 volts. We've seen that a bunch in class, so that's the easier way to do that. If that sits well with you, that's great. If it doesn't, that's fine too. Just do it the hard way. You'll have plenty of time to do that, okay? But I do believe that as you go along that it will become easier to do that. I do want to review the rules for capacitors in series and parallel and just make sure that you have them all in one spot. So the rules for capacitors in series and capacitors in parallel are like this. First is the equivalent capacitance. For capacitors in series, the equivalent capacitance is 1 over C1 plus 1 over C2 plus however many capacitors you have. For capacitors in parallel, the equivalent capacitance is equal to C1 plus C2 plus however many capacitors you have. The second, I'm getting these out of order. That doesn't matter, I guess. The second is that capacitors in series have the same charge. Capacitors in parallel have the same voltage. 3 is that V is equal to V1 plus V2 plus however many capacitors we have. That's what we did up here, by the way, when I said that 6, this should be a 6 volts, that 6 plus 3 volts is equal to 9 volts, that the sum of the voltage is equal to the total voltage. The third rule over here is not really a rule that we use that much, but it is that the charge on the equivalent capacitor is equal to the sum of the charges on the individual capacitors. But like I did in class, I'm going to draw a line through this because it's just not a very useful rule. We just don't really use it that often because capacitors in parallel tend to be easier circuits to deal with anyway, so it's just not a very useful rule. So I list it though just to show that these rules are all really similar. That I'm just, here I have the same charge, here I have the same voltage. Here the voltages add up, here the charges add up. And then finally, for both of these, I have Q equals CV and Q equals CV. Okay, so those are the rules. I've given those to you in class, but just if you haven't memorized those, it's a good idea to memorize them. Put them on note cards, quiz yourself on them, however you go about memorizing stuff like that. And then the circuits are really just applications of those rules. Let's see, I got a student asked a question. Let me look at this text. Sorry, this is a student. Okay. Are there particular questions that y'all want me to look at or you want me to review for you? If not, I'm going to do this other circuit, which is a more complicated circuit, or some other circuit. Is that okay? All right, well, let's do this one, and then, yeah.
So, For spring 2022, we stopped at question 4 with capacitors.
That's right, yeah. So anytime you see a break from capacitors into resistors, that's where you stop. And you'll see it's a pretty clear thing because now I see, one, there's no capacitor in number 5, and it's talking about resistors. So if you've seen resistors, you've gone too far. Look, only 4 questions in the spring 22 exam. Good, easy quiz. All right, it's not going to be an easy quiz, but there's just not much for me to pull from. Okay? So that means, too, that, if there are more difficult questions on the exams, then you're probably going to see those, too, because I have fewer questions to pull from. All right. What is the charge on the 6 microfarad capacitor? Let's think about this, okay? Let's try to do it without writing anything down, although I always encourage you to write things down, but without having to go through all those laborious steps. I know that resistors in parallel have the same voltage. Do you see that this is a parallel branch right here and that this is a parallel branch? Can y'all see that those are 2 parallel branches? If not, let me show you. The reason I know that those are parallel branches is because I have a junction here. I have a point where this wire becomes 2 wires. And then I have another junction over here where these 2 wires become 1 wire. So those are 2 junctions. And in between those junctions, I have 2 parallel branches. I know there are 2 because, well, I have 2 wires here and 2 wires here. So I have 2 parallel branches here and here. I know that across those parallel branches that I will have 12 volts and 12 volts. So if I asked you the question of what is the voltage across the 4 microfarad capacitor, that's an easy question. It's 12 volts, right? It doesn't matter what's going on up here, that the voltage here is going to be 12 volts. Now, I didn't ask you that. I asked you the voltage across the 6 microfarad capacitor. The 6 microfarad is what factor bigger than the 3 microfarad capacitor? By what factor is it bigger? By a factor of 2. 3 times 2 is 6. 6 is twice that of 3. So the voltage across 6, the big capacitors have big or small voltages? Small is right. Big capacitors have small voltages. That means that the 6 microfarad capacitor is going to have a smaller voltage than the 3 microfarad capacitor by a factor of 2. And that has to add up to equal to 12. I just gave you the answer. 2 numbers that add up to 12 that are different by a factor of 2. In this case, that's going to be 8 and 4. All right, we've seen that a lot, and, they're just 12 is an easy number to work with. I will just remind you, and this does come up sometimes on the exam, on the exams, that I don't always have to do a factor of 2, right? So for example, if I had capacitors that were 1 and 3 microfarads, those are different by a factor of 3. Can you tell me that if there was a 12-volt battery attached to those 2 capacitors, what would the distribution of voltages be? 9 and 3, very good. Yeah, so I'd have 9 on which one? On the 1, yeah, I'd have 9 volts and 1 volt. Or what if I had not 1 and 3, but let's say that I had 1 microfarad and 5 microfarads. I don't think this is on any of the tests, but what would that be? I have one that's different by a factor of 5. Actually, does this work? Yeah, this works. Yeah, what would these be? Oh, I feel like somebody's about to say it. I need 2 numbers that are different by a factor of 5 that add up equal to 12. Well, I mean, 2 numbers add up equal to 12. 10 and 2. Very good. So I'd have 10 volts and 2 volts. See, they're different by a factor of 5, but they add up equal to 12. I like to use 12 a lot because, I don't know, it's divisible by 3, it's divisible by 4, it's divisible by 2, and so just be prepared for that number to come up a lot. Okay? So the answer for this one was 4 volts. Oh, that's not the question, is it? So I wanted to know actually what is the charge across that. Q is equal to CV. 6 times 4 is 24 microcoulombs. All right. Let's do another circuit that is a little more difficult. Where is it? This one. This is actually a very similar question, similar difficulty. It just looks different. And students are sometimes get confused about how on number 2, how these 3 capacitors are with respect to one another. Which capacitors are in parallel? C2 and C3 are in parallel. But students will often look at this. I was working with a student yesterday, and they were convinced that all 3 of them were in parallel. Because it sort of looks that way. Well, maybe you're shaking your head, but no, I mean, if this is new to you, it does sort of look that way, that they are all 3 in parallel, because it sort of looks like they are all splitting into 3 branches. But I always start at the battery, and I start traveling through the circuit, and then I see that capacitor comes. And there's been no junction yet. The wire has not broken into 2 pieces yet. But then when I come up here, I see that one wire breaks into 2 wires. That begins my parallel branch. And then over here, these 2 wires become 1 wire. That ends the parallel branch. So another way that we could draw this circuit would look like this. It's another way we could draw that, where I have the 2 microfarad here, and a 1 microfarad, and a 1 microfarad here. So really the hard part in this problem is realizing that those 2 circuits are the same. Some of you will see that circuit, and you'll just see right away that that's what it is, right? But not all of us, me included, think in that same way spatially, that you can take those capacitors in your hand and move them around. And some of you are just that way, and I'm not, and that's fine. But you do need to learn how to see the circuit and identify what is the parallel branch. Octavia? Yeah. So the important part is to look at the branches, where the junctions are. Bless you. Very quiet sneeze. Yeah. All right. I always start at the high side of my battery. That's the positive side of the battery. Just as a general rule, it just helps you to think about circuits. Start at the battery and then start traveling through the battery. Look, when I get to C1, I have not gone through any junction. But then I come to a junction. Notice, by the way, that the same thing has happened here, that I go through that first capacitor before I come to the junction. Then I recognize that junction breaks into 2 parts, here and here. On one part, it goes through C3. On the other, it goes through C2. And then it comes back together again right here. Notice they come back together again right here. And then from there, it goes straight back to the battery, like that. Okay? Now, in the free response part for exam 2, we'll have some that are even more quite a bit more complicated than this, but we'll deal with that as we get closer to that. We've done some of those, but I'll help you with that as we get closer. For now, let's just focus on this. Now, once I get this, I want to find the equivalent capacitance. What am I going to start with? What do I find? What do I simplify first? Right, the parallel. I have 2 1 microfarad capacitors in parallel. They're purely in parallel. There's nothing series in this part of the circuit. So I combine those. That's going to give me, let's see, in parallel, I just add them up. So I get a circuit with 2 microfarads, 2 microfarads, and you probably already see the answer now, maybe, with 12 volts. I know if I have 2 identical capacitors in series, do capacitors in series split or share the voltage? They split it up or they share the same voltage? They split it up, right. And if they're identical capacitors, they're going to split it evenly. So I have 6 volts and 6 volts. And now I can just answer my question, because this is C1 right here. I know the voltage, so I can find the charge is going to be 12 microcoulombs. Q is equal to C times V. 2 times 6 is 12 microcoulombs. What is the voltage across this capacitor? Is it 3 volts? No? What is it? It's 6, right. Capacitors in parallel share the same voltage. They don't split it up, they share it. And capacitors in series split the voltage. In fact, those of you chem majors, when you go into instrumental, or mostly just chem majors, go into instrumental, then you'll build a voltage divider. And a voltage divider in an instrument is something that splits voltages up. It's really just two resistors in series that will split a voltage into two parts. You biologists, if you go into the industry, like you'll work with in labs, and you'll have to learn those things too. But in instrumental, they do some of that. Okay. Oh, let's do number 3 while we're here too, because you're certain to see one of these where I have a circuit that doesn't have any numbers, and that always freaks out students just a little bit. But don't be freaked out. It's okay. Just sort of do it the same way. First, I want to find the equivalent capacitance. I see that I have C1 in series with C2 and C3, which are in parallel. I'm going to redraw this circuit, which would have 2 capacitors in series, 12 volts. This would be C. What would be the equivalent capacitance of C2 and C3? If they're all identical, that is, we just call them all C, what would the equivalent capacitance be? 2C. All right, so I'm just going to have 2 capacitors. I know that one is twice that of the other. In this case, you have to think about the distribution of the capacitance, of the voltages, because there's no numbers to put in, so I can't find the equivalent capacitance. Well, the big capacitor has the small voltage. The small capacitor has the big voltage. They have to add up to equal to 12, and they're different by a factor of 2. So this is going to be 8 volts and 4 volts. And then the voltage across C1 is this 8 volts. So very likely to see a question like that where you don't have numbers and yet you have to find a voltage. Students often struggle with that. Likewise with number 1. Oh, there's some good questions on this test. Number 1, I have a 3 and a 6 microfarad. I don't show you the battery, but I show you what the voltage is across one of those capacitors. The voltage across the 3 microfarad is 12 volts. So then what would be the voltage across the 6 microfarad? Somebody said it. What was it? 6 volts is right. Yeah, so I'd have 6 volts here because it's a bigger capacitor by a factor of 2. So its voltage is going to be smaller by a factor of 2. Right. So on those rules, let's go back and we'll add a little subset of rules where I'll just sort of put it over here to the side. In series, this will be like rule number 5 for series. Big capacitors, big caps have small voltages, and small caps, or small c, has big voltage. There's an inverse relationship between the voltage and the capacitance. That comes about because of this equation, by the way. For capacitors in series, the charge is constant, Q is constant. So if this goes up, that means this goes down by the same amount. There's an inverse relationship between C and V. That's where that comes from, that rule. All right? Other questions that y'all want to look at? Which ones are they?
Why is it only one?
Only 4. Okay. The capacitance of a parallel plate capacitor can be increased by what? The difficult part about this is if you just think about the equations, then you're going to get the wrong answer. And that's usually what we do, is we just think about the equation. You know, this equation, you would say, would be C equal Q over V. And so if you were just looking at that equation, you would say, well, look, if I increase the charge, that increases the capacitance. But that's not really the right way to think about it. I mean, if I think about my bowl can hold so many cherries or whatever. I have a bowl and it can hold so many cherries. If I put more cherries into it, does that make the bowl bigger? No, right? But the bowl is the bowl. It can hold however many cherries it can hold. And if you put more cherries into it, it doesn't make the bowl bigger. So that's why 1 is not an answer. Increasing the charge does not increase the size of the capacitor. Likewise, decreasing the charge doesn't do anything. And so then I'm just left with these 3. And remember, there's a different equation, epsilon naught A over D, kappa, where let's see, if I increase the plate separation, that is if this goes up, that means that would go down, so that's not it. If I decrease the plate separation, that is if that goes down, then yeah, that'll go up, the capacitance. So 4 is right, 3 is not. And if I decrease the plate area, if this goes down, then this also goes down. So only decreasing the plate separation in these options will give you an increased capacitance. That was a difficult question. It seemed easy, but the difficult part was understanding that increasing the charge does not increase the capacitance. That's probably what you were thinking, right? That was one of the answers. And mathematically that is true, but physically it's not true. You can't make my bowl bigger by putting more stuff into it. Good question. I like that question. Oh goodness, let's look at number 5 while we're here, okay? Because students struggle with this. Again, this is one of those, can I move things around in my head and think about different ways to represent this circuit? You know, if you ever look at a circuit diagram where you get something like your radio or whatever, and you look and go, whoa, that looks weird, because they try to fit all those different devices onto the smallest grid as possible, and so they'll draw them in ways that you might not draw them otherwise. In this case, I want to know what is the equivalent capacitance between this point and this point. Notice there's no battery. If you want to think of there being a battery, you can imagine that there would be a battery right there. Okay, but I don't need to have a battery in order to have a capacitance. Like in lab, when y'all used the breadboards and you were finding the equivalent capacitance, you weren't using a battery in that case. You were just using the capacitors. And so a similar thing here. So how do I draw this? First, I want to ask how many parallel branches are there? You know, I have a junction right here where one wire comes in and becomes how many wires? It becomes 3 wires, right? So I have a parallel branch, or a parallel branch that has 3 wires. The middle wire only has 1 capacitor, and then the other 2 wires have 2 capacitors. So that's what I want to know is what is the equivalent capacitance. Each of these are 4 microfarads, 4 and 4, 4 and 4, and 4. Now I know a 4 and 4 microfarad in series, that has an equivalent of what? Y'all remember? 2, right. Remember that's one of my pairs that I like to use. 1 over 1 over 4 plus 1 over 4 is 1 over a half, which is equal to 2. Practice those so you don't have to futz around with your calculator on the test, okay? Because you'll be faster, you know. There aren't that many pairs, 3 and 6, 4 and 4, 3, 3 and 3. That's 1 over a third plus a third plus a third. When we get to the exam, we'll see as you're practicing, there are some others too. But those are the most common ones. So I have 2 microfarads, 4 microfarads, and 2 microfarads. In parallel, I just add those up. 2 plus 4 plus 2 is 8 microfarads. Okay? That's a difficult question just because it looks different than the circuits that we've been drawing. And so, again, I find that with this chapter and in a couple of chapters when we do magnetic fields, that it's really going to stretch your spatial skills, your ability to see things in different ways. So I like these chapters for that reason. Okay, other particular questions? How y'all feeling about this quiz? Feeling okay? Yeah, I'm feeling pretty good about it. I've had a few students in my office the past few days, and you know, they came in thinking they were struggling, but then after they spend 5 or 10 minutes, they say, hey, this isn't really that bad. So if you're feeling that way, like you feel like you're just not really understanding, come see me or take some time over the weekend, spend 30 minutes practicing all the various problems, and you know, see how you feel then. Practice more than 30 minutes. Like I'd really love for you to spend a couple of hours. That'll probably allow you to work each problem 2 or 3 times in a couple of hours. Use the videos, but only use them as a help, not as a crutch. So work the problems on your own at first, and then if you run into a difficulty or if you get the answer wrong, then you go back and look at what you did wrong. So that's the way the videos are intended to be used. Y'all do use the videos though? Yeah, they're helpful? Yeah, okay. They're entertaining? Seriously? They're not entertaining. All right, Chastity. Never mind. Okay. So, other questions? What are we going to make on the quiz? That's what I want. I would love to have an average of 90%. That would be really high. I think the average on the last quiz was like 85. Is that right? It was pretty high. But I want, my quizzes, like, I want y'all to do, it's gonna be like the thing that saves your grade in the course. That's what I want. That's really what the quizzes are meant to be, to save your grade in the course, and they help you prepare for the exams. So it's really what I want. That's my intention. Okay? All right. Well, that's all I have. Make sure you stop by. Just make sure I didn't get everybody. Stop by. Make sure I got your name.